Now let's go to next title. EMF induced in a conducting rod moving in a uniform magnetic field. That is motional EMF. Let me share one figure. In this figure, there is a conducting rod which is initially in a region of magnetic field and is at rest. That is not moving. And so there is no potential difference created between the ends of the conductor, because the free electrons in it does not experience any force in this case. What would happen if that conductor is moved in any direction in that field? Let us check. Okay, this figure shows the same conductor which is moving with velocity v to the right in an inward magnetic field. As it moves, the free electrons in it experience downward Lorentz force. Because of this, the lower one end will be negative. The lower end will have negative charge density and the upper end will have corresponding positive charge density. So there is potential difference created between the two ends of the conductor. Upper end is at higher potential, lower end is at lower potential. Now this conductor behaves as a battery. As long as it remains in motion, it will behave as a battery. And if we connect this conductor to external circuit with a load, the induced current will flow through the circuit. Now, one important thing to remember here is that as the electrons shift downward, the induced electric field will exert upward force on those very electrons. As the number of electrons shifting downward increase, the upward force also increases. The magnetic field is exerting downward force, while that induced electric field is exerting upward force. So there is a kind of tug of war between two forces. One due to this applied magnetic field and other due to the induced electric field. At some point, the free electrons will attain steady state, that is, they will be in equilibrium when the downward force due to magnetic field is balanced by upward force due to induced electric field. The potential difference created for a given magnetic field strength is maximum in this condition of equilibrium, and that potential difference is called the motional EMF. Remember that. The motional EMF is the maximum potential difference created due to the motion of a conductor in magnetic field for given value of magnetic field. If you increase the magnetic field, the downward force or the downward Lorentz force will increase, and further potential difference can be increased, and that would not be maximum value. Which potential difference is called that motional EMF? Only the maximum value. So for a given magnetic field strength, the potential difference created between the ends of the conductor due to its motion is called the motional EMF. Yeah, what I have explained is all written in the paragraphs over here. Let me share. Yeah, again, I want to tell you, you can copy if you think it is necessary from the very slide. Now let's derive an expression for motional EMF. Let's consider a rectangular rail of wire over which a straight conductor of length L slides to the right, and that rectangular coil is placed in a uniform magnetic field, inward magnetic field of strength B. As the conductor shifts to the right, the free electrons in it experience downward Lorentz force. Free electrons shift to the lower end. And if we consider for our convention, the positive charges would shift to the upper end. When the conductor shifts from position CD to EF by moving a small distance dx in very small time interval dt, then the velocity of the conductor can be written as dx by dt. The work done on the conductor, the work done on the positive charge plus q to move it through the length of the conductor can be calculated, because the force acting on it is the Lorentz force. The magnitude of Lorentz force is given by bq sine theta. Here theta is 90 degree, because the conductor is moving perpendicular to the magnetic field. Conductor is moving to the right horizontally, and the magnetic field is vertically inward, that is perpendicularly into the plane of vapor. And the work done is the force, magnitude of force times the distance moved by the charge. So work done is equal to BQVL. Now from the definition, an EMF is work done per unit test charge. And from the previous expression, if we substitute, we get induced EMF is equal to BVL. That is E, motional EMF E is equal to BVL. And if R is the total resistance in the circuit, the magnitude of induced current is given by, again by using Ohm's law, as I is equal to E upon R, or BVL upon R. And the induced current may cause some loss of electric power in the form of heat. That is called Joule's power loss, which is given by E square upon R, or B square L square upon R. From this same condition, from a conductor sliding over a rail of wire, we can deduce Faraday's law. According to Faraday's law, I want to remind that according to Faraday's law, the magnitude of induced EMF is equal to rate of change of magnetic flux. Let us say check what the change in flux linked with the conductor gives in this condition. The flux change is caused by the change in area, say area swept by the conductor, which is a rectangle. So change in area or area swept can be denoted by del A, or without giving symbol, we can write flux change is equal to B into change in area. Change in area here is just the rectangle CEFD or CDFE. That area is equal to length into breadth, LDX. So flux change is equal to BLDX. Now the rate of change of flux is then given by dϕ by dt is equal to BLDX by dt. That dx by dt that we have already written is just the velocity of that conductor. So the rate of change of flux is equal to BLV. And this BLV is just motional EMF. That means the rate of change of flux is equal to motional EMF, which is Faraday's law of electromagnetic induction. We may attach the negative sign to represent that induced EMF opposes the flux change. Or otherwise, you must know you have already deduced the Faraday's law.